when we have something like phosphorus and we're looking for the electron configuration, what we're asking is, what would happen if you took the nucleus for phosphorus, here are the protons, and then allowed all the electrons to come in one at a time? How many electrons would there be in phosphorus? Yeah. Everybody knows, but nobody wants to say it. 15, that's right. 15 electrons. So there's 15 electrons. We're going to let them in one at a time. And the first electron that would go in, we would say, would be like hydrogen in terms of its location around the nucleus. And that location would reside in the n equals 1, the first shell, right? N. And the n quantum number corresponds to a couple of things. What did we say n corresponds to? The energy and the distance from the nucleus, which is kind of the same thing, because the farther you get away from the nucleus, the more energy you have. Remember, we said that if an element or electron is far away from the nucleus and then all of a sudden it can zoom in close because there's a vacancy, that would release a lot of energy. The photon that would be released would have a very small wavelength, high frequency. Okay? So, n equals 1, and the first shell in n equals 1, if n equals 1, L can equal what? What are the possible values for L if n equals 1? 0. Now remember that we have some letters that help us correlate L. L equals 0, 1, 2, 3. We have some letters for these, right? What are the letters? S, P, D, and F. Okay? So we also know that those correspond to certain blocks on the periodic table. All right? Our S block is just these first two columns, S block. Our P block are these 6 columns. Our D block are our transition metals, and the F block is our inner transition metals. So we say that the first electron, the one that would be kind of similar to where hydrogen's electron would be, is in a 1s orbital. But phosphorus doesn't just have one electron there, it has a second electron there. True? So there's going to be a total of 2 electrons in the 1s orbital. And we can follow along on the periodic table because the n value 1 corresponds to the row. So now, next, after we have 2 electrons, this represents 1 electron here and then a second electron here. And this is not just a circular, this is actually a spherical shape, right? And that's what that L value tells us. If L is equal to 0, S is going to be used to remind us of spherical. Okay? P, what shape does P correspond to? A dumbbell. Now, this is also 3-dimensional, right? So don't feel like this is just some sort of a figure 8. That's a horrible drawing. Let's try again. There we go. Okay? So just like N corresponds to distance or and energy, L corresponds to shape. Whoops. All right. The d orbital, they look like this for the most part. And f orbitals look like that as well. Whoops. I'm not going to keep that up there. It's a 3-dimensional lobe, or it has twice as many lobes as this, but it's 3-dimensional, so one coming out and one that way. Okay? So, N corresponds to distance and energy, L corresponds to shape, and there's a small energy component as well. So just a little bit of energy. So when we'll talk about that in the future. Okay? M sub L is not, and that's the next quantum number, is not used in the electron configuration, but it corresponds to the, did anybody remember? The orientation the orientation of the orbital. So for n equals 1, L equals 0, what's the possible m sub L values? All right. It's just 0, right? If L equals whatever, m sub L will be positive whatever, negative whatever, and all the numbers in between. So if L is 0, then this only can be 0. And that should be consistent with the idea that a sphere cannot be oriented any other way around that origin, right? If I spin it or twist it, it's not going to be any different. However, for L equals 1, we're talking about our p orbitals now, right? L equals 1, p orbitals can be oriented different ways, and the possible m sub L values when L equals 1 are what? And positive 1, right? All of those which represent or correspond to the p orbitals going on x, y, and the z axis, right? Okay? All right. So, 1s2. Right now, if we were to stop, our electrons look a lot like what? Well, we got 2 in there, though, right? So we're on helium. So we can use the periodic table to know what's next. Next is supposed to be lithium, and lithium is the second row, so that's going to be 2. Our n value is going to be 2. It's in the s block, so the L value is going to be 0 still, 2s. And because we're going to phosphorus, we're going to have to fill it up. We're going to have to put 2 electrons in there. Okay? So if I were to draw this second spherical shell, right? 2 electrons in there. So now there's the 1s inside, 2 electrons, and then a 2s inside, or outside, with 2 electrons. Okay? So, what's next after the 2s2? Where do we go now? 2p. We're starting at boron, right? And we need to fill up all 6 spots. 2p, 6. All right, now that represents elements boron to neon, right? 2p6. Okay? If we stop now, we'll be at what element? Neon. And you can always count your electrons. That means we should add up to 10 electrons. 6, 7, 8, 9, 10. Right? But we want to keep going. So what's next after neon? 3. 3s2. Whoops. 3s2, and then what? 3p3. Just going to aluminum. Or sorry, phosphorus. Just going to phosphorus. 3p3. So that is the electron configuration for phosphorus. We see that we have 2 electrons in an n equals 1, L equals 0 orbital, 2 electrons in an n equals 2, L equals 0 orbital, 6 electrons in an n equals 2, L equals what? What does L equal here? P, which corresponds with what number or letter? Yeah, number? 1, right? And then 2 in n equals 3, L equals 0, and then 3 in n equals 3, L equals what? Just 1, right? P is 1, is that right? Okay, very good. So that's the electron configuration. If I wanted to draw these, wait, I didn't draw the 2 P's, right? There's 2 electrons in each of these orbitals, right? 2 electrons in each orbital, total of 6. After those 2 P's, we need a 3s2. It's spherical again. See, and then we have our 3 P's. There's 3 3p orbitals, a total space for how many electrons? How many electrons could I fit in 3 p orbitals? So it's like from aluminum to argon, how many electrons would fit in that subshell? 6 across there, right? Aluminum, silicon, phosphorus, sulfur, chlorine, and argon, right? 6, and that's consistent with 2 electrons per orbital, right? But I only have 3 in the 3p here. See, it's really clear, right? Easy to understand what's going on there. It's just a mess. Doesn't make any sense. But I only have one electron in each of these outer 3p orbitals. And let's pretend like this is a fan. And it's spinning and it's cooling me off, right? Does that make sense? Yeah, it's not one-dimensional. It's three-dimensional, so it's not going to actually behave like a fan. And the atom doesn't hold still. It's tumbling, right? So the whole thing is... But let's pretend like the whole thing is swirling, right? And I bring my finger in to touch it. You got to tell the kids, don't touch the fan. You're going to lose your finger, right? So they come in and they touch the fan. What are they going to hit first? What's going to hit them? Which orbitals are going to hit them first? The largest ones, which in this case are the what? What is this one again? The 3p. The 3p. 3p orbitals are the thing that's going to hit them. Because they're swirling all over the place. If I had this thing spinning like crazy, what would it look like if I had it on top of my hand? What would it look like? It would be just a sphere, right? If it was spinning all over the place, it would just look like a sphere. Okay, so, yeah. My goodness. I don't know if I have any more. I gave out 3 extra last class. Did you... Oh, I do. Praise the day. Nobody else needs one, right? Chapter 8. You need chapter 8? Yep. Oh. Let's see. I do have 1 extra. I have 2 extra. Anybody else need one? Chapter 8? I'm going to pass that back for him. Okay. So then, let's see if we can write an electron configuration for an element. Okay. Now, we said that there was something sneaky when you started entering elements past scandium. Do you remember what we said last time? When we start getting into scandium? Oh, no. But you're talking about the abbreviated electron configuration where you use the noble gas. And that's worth talking about too. So let's finish that conversation first. If I wanted to write the abbreviated electron configuration for phosphorus, I would use the most recent electron configuration, 3p3, right? The abbreviated version would go back to the first noble gas, closest noble gas to phosphorus. What is that? Neon. And then I would just start from there. Which would be what? What electrons? 3s2, 3p3. All right, so that's the noble gas electron configuration. And this tells us an important separation. What do we call these electrons here? What do we call those ones? These ones are called the valence electrons. And they're important because those are the ones that the element is generally going to do chemistry with. Either lose these elements or try to fill up its outer shell. These ones are called core electrons. And usually the element, not usually, I mean, you won't see chemistry where the element digs into these electrons. That's stable, right? That's a noble gas configuration, it's stable there. So it's just the valence electrons that the element would like to wheel and deal with. All right, so let's see if you guys remember the surprise that we had right before last class, and see if you can give me we'll do the noble gas abbreviated electron configuration to save ourselves some time. Is that okay, or do you guys feel like you should do one that's not noble gas first? How about we do both? One that's not noble gas abbreviated, and then one that is noble gas abbreviated. All right, so electron configuration for iron. Electron configuration for iron. Abbreviated and unabbreviated. Did everybody get the roll? I got you. Anybody else? Okay. Okay, go for it. Abbreviated and unabbreviated electron configuration for iron. So it's going to start off just like phosphorus, right? Because all the electrons that are in phosphorus are in iron. So if you're lost, you can at least get up to phosphorus. For one of them, we're going to, right? That's going to. We have one that we want to be just the regular and one the abbreviated.
All right.
So if you want to start with there, that's fine.
I just think, okay, okay, thank you.
SC, scandium, you mean, or 19 and 20, or what are you talking about? Yes, that's right. That's right. 4s2, 3d6. That's right. Good. Very good. Now, do you know how to write out the whole thing if you needed to?
Yes.
Okay, good. Good. Okay, so what is the n value for that D row? Do you remember?
The end value.
Yeah, because that's what those numbers are. 1, 2, 3. Those are actual n values, right? So for our, if you start off at argon and try to work your way to iron,
Yeah.
so the next element is number 19, and we can know its n value by looking at its row. So what row is it in?
3 or 4?
4, right? Hydrogen is 1, lithium, sodium, potassium, right?
Yeah.
So 4, and it's in the S block. You understand what that means? So 4s, and then there's 2, potassium and calcium.
Okay, and that's that little number right there.
That's right, 2 electrons in the 4s.
And then you go to the.
Now we go to the D block, and we would want to say it's 4D, but remember last class we said right before we left that
It's 1, right?
no, it's 1 less than 4, so it's 3, 3D.
Oh, okay, so that's 3D. And then do you count over?
Yes.
6.
3D6.
Is that right? To
That's
start
right.
with argon, or do you have to start with another noble gas?
If you're going to do the noble gas abbreviated electron configuration for iron, that would be it.
Okay.
But you would know how to start from scratch too if you wanted to, right?
Well, you start at the very top, right?
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right?
And then it would be that.
Yes.
Okay. Okay. I'm starting to feel.
Looks great. Yeah, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Good.
Could I use that as a noble gas?
That's the one you'd have to use, yep. That's exactly right. Good job. Okay, good. 4s2, but this, right before class ended last class, we said that when you go into the D, you actually have to have n minus 1, yeah. So there's the 3 there, and that's it. Very good. You following along? Good. Good job. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we go into where, if I were to stop right now, where would I be? Calcium. All right? So how do we know that fast? Well, fourth row, S block, 2 electrons, that's potassium and calcium. Can everybody see that now? All right. So we want to go to iron, and we start here at scandium. We're in the D block now, and we said right before class ended last time, that our n value isn't 4 when we enter the D block on the 4th row, but it's actually just 1 less, so it's 3. So it's 3D, and then we count across, and there's 6 electrons, right? If we are doing the noble gas electron configuration, then we would just do argon and pick up from argon, 4s2, 3d6. In both cases, though, we need to be able to identify our Valence electrons. What are the valence electrons? How many valence electrons in iron? Okay? Valence electrons are the ones that have the highest N value.
Wait, can you repeat how many electrons?
Valence electrons, they have the highest N value. So here, these were the valence electrons because the N values here were both 3. N values are 3, 2, and 1, right?
I don't know how to find the N value.
N value, you don't know how to, so when you say like, we look at magnesium, for example, see magnesium? All right, it's on the 3rd row, so we say its N value is 3. So the last electron in magnesium, it has an N value of 3. Okay? In terms of when you write it up here, that number that you're writing, 1 in the 1s2, is the N value. So 2N equals 2, 2p6, N equals 2. And that N value corresponds to the distance and energy of the electron. Distance from the nucleus and energy.
Why is it 8?
Why is it what?
Why is it 8?
Oh, it's not. It's not. The answer is actually what? 2. There's 2 force 2 electrons. These ones we call pseudo-valence electrons because sometimes chemistry is done with them, but not the first chemical interaction or the chemical reactions are going to be done with our valence electrons. Okay, so I feel like we probably can mostly identify what a electron configuration for elements should be. I think we're gaining an understanding of what our quantum numbers are, our M, L, M sub L, M sub S values. Now I want to get back to this energy diagram. Energy diagram to plot out the energies of our orbitals, all right? So, if I want to draw this thing, if I want to draw what the atom looks like, right? It'd be a mess again, but something spherical, 1s, something spherical, 2s, 2p, right? Something spherical, 3s, 3p, something spherical, 4s, and then 3d, we have this little thing, looks like that. All right, so, it doesn't help to draw it out after that point, right? But that's the idea here. This isn't very helpful, so we use this energy diagram to kind of draw a picture of the atom. So instead of drawing an actual orbital with the shape, we just draw a line and say that's my 1s, and that's the relative energy for that 1s. The next orbital that would be filled is the 2s, and it's higher in energy. After the 2s is the 2p. Now, it has the same n value, but it's a little bit higher in energy. It's a little bit higher in energy. And these 3 marks here represent the different orbitals, right? The p orbitals look like this. And so we could call one of these px, py, and pz if we wanted to in terms of the axis that they're on. All right? I won't leave that in there. But that's why there's 3 of them. So 2 is our n value in this little schematic. P is our L value, right? And then these, either x, y, or z, -1, 0, or +1, are our M sub L values. Can you see that okay? And then when we fill the electrons up, we draw a little arrow, like that. And we indicate that it's a +1/2 by pointing up and a -1/2 by pointing down. So I can draw this sort of thing, and you could say, if I stopped right here, what element does this energy diagram represent right now? Boron, right. I have 5 electrons. The last electron is in the 2p, right? The electron configuration, 1s2, 2s2, 2p1. Can everybody see that okay? So this is an energy diagram to help us kind of think about that mess, right, that we really can't visualize and draw very well, a little more spread out and manageable. After we get 2p, what's next? If we had more electrons here, what would be next? What's after 2p? 3s. How do we know? Well, you can just follow along. You can look at 2, p ends at neon, and then see that sodium's next. Third row, 3, it's S block, S. So 3s, there it is, and then it's 3p, and then it's 4s, and then it's 3d. All right. Now, how many of these little, what do these little things represent again? These little dashes that I'm writing? They're the orbitals. These little lines, these arrows are the electrons. But that's right, there should be 5 going across here because there's 10 spaces for elements, right? From scandium to zinc, or 5 orbitals in that subshell. Or, right, another way to think about it is if n equals 2 and L equals 1, then m sub L can equal, no, sorry. If n equals 3 and L equals 2, m sub L can equal what? Positive 1 and positive 2, right? Which is 1, 2, 3, 4, 5. So that's what these 5 are, right? So the n value is 3. The L value is what? What's the L value that corresponds with the D? 2. 2. Okay? And if you ever forget, you can look at the periodic table and remember that we start at 0, and that's all you really got to remember. S block, 0. P block, 1. D block, 2. F block, 3. Right? So when L equals 2, m sub L, there should be 5 different possible values, -2, -1, 0, 1, and 2. They're all the same energy, though. Those values just represent what? What does m sub L represent for us? Indicate for us? Orientation. The orientation of our d orbitals. Okay, there we go. So if I wanted to fill in electrons enough to make it this thing represent iron, right? I already started with 1s and 2s, and now I'm going to start filling the 2p. And you have to remember, it's called Hund's rule. You don't really remember the names, so necessarily, it's not a big deal. Just remember that electrons have to fill up orbitals completely before they begin to pair up. What did I say this up and down arrow represents here? What's that? Electrons. Yep, they represent electrons. Why did I draw one up and one down? That represents our m sub s value. Do you remember what m sub s can be? That's right, either -1/2 or +1/2. And so this is +1/2 and that's -1/2. All right, so filled up the 2p. Now here comes the 3s, and then here comes the 3p. Hund's rule, fill them up one at a time. Here comes the 4s. Now how many electrons for iron in the 3d? 6. So I go 1, 2, 3, 4, 5, 6. All right, there we go. So we have our orbital diagram here for iron. Okay? Again, what does this do for us? It allows us to see this without having to see it all overlapped like that, right? I used to think, if you just show it to me once, I'll be able to figure it out. But that doesn't help. To look at that, right? I made this when I first started teaching, but it doesn't, it doesn't really help. So this is the idea, though. There's the nucleus, and here is one electron in a s orbital, right? So this you could think of as the 1s orbital. And I even have an electron moving around to make you feel good, like there's a little particle doing something, right? Yeah?
It's actually it's not following a pattern, right? It's just going to the sphere.
It's not even there. It's not even there, right? It's not a particle. It's actually just a sphere of electromagnetic wave, a three-dimensional wave. But I drew the particle because it makes us feel good, right? So now there are ways that you can kind of detect it and make yourself feel like, I found the particle, the electron. This is where it's at. But yeah. So after I put a second electron into 1s, I need to bring in my second shell. So the second shell is going to contain a 2s and a set of 2p orbitals, right? The first electrons go into, the first two electrons go into a 2s. There's our second electron in the 2s. And the next one starts to fill in 2p. There it is. It's going back and forth in one of the p orbitals. The next one goes into a second 2p orbital. There it is, going up and down now. So we had one on the z-axis first, now we have one on the y-axis. And then we'll put a last one, a third one, into the x-axis. So now we have 2 in the 1s, 2 in the 2p, and 2 in the 1s, 2 in the 2s, and then 3 in the 2p. So what element is this? 3 in the 2p? Nitrogen. Very good. So we have a nitrogen atom. So how many more do we have room for in the 2p there now? 3 more, right? 3 more electrons. So, whoops, we'll fill them up, and, doesn't look much different because the electrons all went into that same subshell, right? Now, if I'm going to bring in some more electrons, I'm going to have to bring in a whole nother shell, right? And it's going to be a 3, n equals 3. So it's going to have s, p's, and d's, right? So I'm going to have to shrink this down a little bit. Here's my 1s. Here's my 2p. Whoops. Here comes my 2p, or sorry, my second shell, 2s and 2p. And then here comes my third shell with the 3s, 3p, and 3d orbitals. And so then we throw some electrons in and let it do its thing. But again, it becomes kind of less, not less intuitive, but less helpful, right? If I just threw that up there and said, there it is, good thing we understand it, right? But this parses it out and puts it into little sections so that we can understand what's going on. Okay? And we also can see something here. What element was this again? Iron. We're dealing with iron. And up till now, we've always said, if I buy some iron chloride, I have to indicate to you what? If I say, I went to Walmart, I bought you some iron chloride, you're going to say, what kind, right? Because I could have bought iron what? 2 or iron 3. Now, why is it iron 2 or iron 3? Now, we haven't ever talked about that, right? It's a bad thing to talk about. Some things you just don't talk about, right? But we're trying to get to a point where we can answer that. And our explanation for why iron 2 forms is because iron has 2 valence electrons, all right? And so if I'm going to make this a +2 charge, I'm going to lose those valence electrons. Those were the highest energy. Those are the highest energy electrons. And by losing them, I stabilize the iron atom into an iron ion. Now, why is iron 3 stable? Well, if you look at this, if I look at this, see, if you look at this, I don't know what you see. But when I look at this, I see one, right, it's pretty, but there's one really ugly part. Can you see the ugly part? Yeah, this one right there, right? Why are you here? You're not welcome here. If they were gone, right, look how pretty it would look. See that? Doesn't that look symmetrical, right? And there is some stability that's earned, that the system can releases energy if you have a completely half-filled subshell like that, especially the d orbitals. And so That's where we get our stability to form the iron plus 3. What would the next charged species need to be? We'd have to lose how many electrons now? We'd have to get rid of all those to completely empty the shell, which would be an iron plus what? 8? Right? No. Yeah, 8. Iron plus 8. And that's just too many electrons, so you don't see it. So the ions that we do see are an iron plus 2 and an iron plus 3 because of this electron configuration and orbital diagram that we have here. Okay? All right. Where are we at? Great. Now we can have conversations about things like the size of atoms. Oh, look at this. This is interesting. Our s orbitals look like this. Whoops. Let's make it a little bigger for us. You remember when I was swinging that rope around? We were swinging that rope around. We were playing jump rope with it. And if we swung it fast, it made 2 regions of kind of energy. And if we swung it even faster, we had 3 regions. Remember that? And we said that those regions in the middle where they were, that looks horrible, especially if you weren't here for that day. Let's try again. Fixed wave, right? Or we could do this, right? We called these regions right here where there was no motion, what do we call those? Nodes. And 1s has a node in there, 2s has 2 nodes in there, 3s has 3 nodes. So the spherical orbital, which is the 3s, for example, has these regions of electron density and these areas where there is no electron density. Again, because this is a 3-dimensional modulating wave, right? Okay, here are our shape for our, remember that cool video? Here are the shape for the p orbitals. I've drawn them a couple times for you, so that shouldn't be a surprise. Here's the shape for the d orbitals. I haven't drawn for you because it doesn't do service for me to draw them very well. And we're not going to talk about why this one looks like that. But these are essentially shapes that the equations will draw out, the wave function equations will draw out for you. Okay? Now, let's have a conversation about what it's like to be in a big family, to be the last kid, and to walk around the mall. Right? Have you guys ever walked around the mall as a big family? Anybody have a big family? Yeah? Cool. I was the 10th child. Now, not everything I say here is true, but it's just, to help you understand what's going on. I was the 10th child, and when we would walk around the mall, I was the youngest, and so it was really easy for me to get lost because my family already had 9, and they were so relaxed about what I did, right? And when we walked down the mall all together, this never happened. There's never all 10 of us together like that. But if we ever walked down the mall, the parents would be in the middle and they'd be saying, hey, stop, don't touch that. Hey, come here, leave that alone. And you'll have this experience. And the swath that you would take is relatively large, right? Especially if you have 10 kids. If you just have 1 kid and you're walking to the mall, then your swath is really tiny because you just can watch that child the whole time. And if they come close to anything, you say, stop, come back. Hey, don't touch that, right? And so the swath is very small. And what you call, or what this relates to, is the size of our atoms and what we call the effective nuclear charge, how much of the protons, the electrons are actually kind of interacting or feeling, that charge that they're feeling, due to the shielding effects. So if I have 10 kids, the 10th child doesn't receive as much attention as the first children do. And the outer edge electrons are higher in energy, and thus they're farther away, and they're also easier to kind of eject off of our atom. Okay? So if we look at the size of atoms, they get bigger as you go down, and that's not surprising. There's just more electrons going out. What might be surprising is, though, if you look at the trend of size increasing mass from left to right across our shells, the atom's size actually decrease. The atom size actually decrease. And that's because when you go from potassium to calcium, you're adding an electron. Potassium's electron 3s1, right? And the calcium, the next electron, where is it going? What orbital is it going into? 3s2. So it's basically the same. It's 3s. It only decreases in size because there's another proton that's added as well. And so it can get smaller in size. Looking across from scandium to zinc, 3D. Wait, did I just talk about this one? Oh, sorry, that's 4s2, 4s, right? 4s1 and 4s2. So looking at scandium going across, right? All of these electrons are going into what subshell? The D subshell, the 3D, right? All are going into 3D. And so you add one in, it's not getting into a larger subshell, it's in the same subshell, it's just filling it up, but there's more protons, and so the electrons get pulled in tighter and tighter. So size increases as you go top to bottom, but it decreases as you go left to right across the subshells. Once you enter this subshell, you get a slight increase here, but then you get a decrease as you go across. All right? Question? No? Now, what happens if you're at the mall, just you and your spouse and your 5 kids, but then you have a 6th kid, not yours, but some neighbor kid that comes with you to the mall? How is that going to increase